Dr. L. Jones Tarsius Das, Professor of Mathematics, College of Engineering Gindi, Anna University, Chennai. He has obtained BSc and MSc Mathematics from Madurai Kamaraj University and PhD from Indian Institute of Technology, Bombay. He has served as NBHM Postdoctoral Fellow at Indian Institute of Technology, Bombay, and then as visiting faculty at University of Tennessee, Knoxville, USA, and Colorado School of Mines, Golden, USA. He is currently working as a professor in the Department of Mathematics at Anna University, Chennai. His research area includes numerical analysis of ordinary differential equations and partial differential equations. He has published more than 25 research papers in reputed international journals. He has visited many countries like USA, UK, Italy, Malaysia to participate in international conferences. He has completed DST SCRB funding project.
Welcome to UGC lecture series on computational mathematics, practical laboratory course for BSc Electronics honors students. Today in the series we are going to see numerical solution to ordinary differential equations. In this lecture we are going to discuss two important methods, Euler's method and Runge-Kutta method. The two fourth order Runge-Kutta method we are going to discuss. The problem of consideration, that is the initial value problem. Initial value problem consists of two things, one an ordinary differential equations and an initial conditions. This is the ordinary differential equation, y derivative, dot indicates the derivative and f of t comma y. Okay. So, given the right hand side function f and the starting point y naught, we wish to solve this equation, the initial value problem consisting of first the differential equation and then the initial condition. Here f could be any function of two variable t and y naught is the condition. Y is a function of t as a solution, it can be function of t or function of x. So, how to write any first order differential equation in the following form, dy by dx and f of x y. Here x is the independent variable, y is the dependent variable, depends on x, it is y equal to y of x. So, the derivative of y is given in terms of function. For example, takes this differential equation dy by dx plus 2y equal to 1.3 e power minus x, and the initial condition y at the starting point 0 is 5. So, this is the differential equation, this is not in this form. So, how to write this the second equation in the first form? So, you can rewrite, take the y part to the right side. When you take the y part to the right side, the equation is rewritten in the following form, dy by dx equal to 1 minus x minus 2y. The initial condition is not changed. Now, I keep the right hand side 1.3 e raised to minus x minus 2y as a function of x and y. Now, this is the differential equation we are given. We would like to convert this equation in the form. So, how to do that? This 2y part you can take it to the right side. Now, it is of this form and you can notice that the initial condition is not changed, only the differential equation is also not changed, but the form is rewritten in a different way. Now, I can write the right hand side the entire expression as the given function f of x y as 1.3 e raised to minus x minus 2y. In this manner, any differential equation, only the derivative term you can keep in the left side, all the remaining terms can be taken to the right side, and that can be expressed in this form dy by dx equal to f of x comma y. The main method which we are going to see first is the Euler's method. It is named after a famous mathematician Leonhard Euler, and basically the idea behind the method is y is expressed in terms of derived slopes. So, what is slope? Slope is the rate of change of y to the corresponding change in the x. So, it is basically how the function is rising and based on the x differences that the run. So, y 1 minus y naught and x 1 minus x naught. Here y naught is nothing but the initial condition, x naught is nothing but the initial point. So, basically the next point y 1 the first time level and x 1 is the corresponding the time level. So, when we write the slope in the following form, the given problem is dy by dx is f of x y. What is dy by dx? Basically the slope. So, this should be equated to f of x comma x naught y naught, and if I try to solve that, the same thing I can rewrite as y 1 minus y naught is equal to x 1 minus x naught times this the f. Again that can be rewritten as y 1 is equal to y naught plus f at x naught y naught times x 1 minus x naught. Assuming that this is nothing but the difference between the initial point and the current point. So, we call it as the parameter the step size h. So, y 1 the function value at the first time level is computed approximately as y naught plus f value at the previous point times h. Here y naught is known because that is the initial value, x naught y naught are also known and a step size is known. So, this kind of method is called the Euler's method. This can also be obtained by integrating the given differential equation from x naught to x 1 and replacing by the left point rule. So, you get the same thing. The geometric meaning of Euler's method is that this is x naught, this is x 1. So, we would like to compute the y value, the true value at x 1, but rather we are computing the predicted value, the approximate value, and this is basically the geometric meaning of Euler's method is the tangential approximation. So, the geometric meaning of Euler's method is we just at the initial point we draw the tangent and where it will meet the vertical axis x equal to x 1, where does it meets, that is the approximate value of the obtained by this method. Once again it is repeated. Similarly, for a general point x I and this is the current point x I plus 1, this is the previous point x I and this is the current point x I plus 1. So, our main aim is to compute the solution value at x I plus 1. This is the true value which is we are not going to compute, rather we are computing the approximate value y I plus 1. So, what we do is we take the tangential approximation. So, basically this is the tangent line where it meets this vertical line, that is the approximate solution of y I plus 1. Euler's method is basically tangential approximation, and that method is given in terms of a general point y I plus 1 is knowing y I the previous approximate value of y at x ith point and the corresponding f value at that point, and h is the step size, we compute the present value. Once again I will just explain the method. Knowing the previous value y I, that is the approximate solution value at the x ith point, we would like to compute the approximate value at x I plus 1th point using this equation. Here y I is known, f expression is known, at x I minus 1 that is known, h is also known, only unknown is that. So, such a technique is called an explicit method, and it is also single step method because you have only two time step, the x I and x I plus 1. Here x I are referred as time step, though we use x variable notation instead, rather t, we call it as time steps. You have it, this expression involves only two time steps, that is why it is called two single step method. Knowing this, you have only one unknown, so it is a single step method. I also mentioned that if this is the problem, using numerical integration also one can obtain the method. There are two interpretation, one is the geometrical meaning, another one is numerical integration. Basically integrate this equation from x k to x k plus 1, and if I integrate this and derivative will give you the antiderivative is y k plus 1 minus y k, and that will give you this equation, and basically we get the Euler's method. Knowing the previous values, we compute the current values. Now, we go for an example, a very simple example, y prime plus 10 y equal to 0. So, taking this to the right side, I get minus 10 y. So, the derivative is proportional to the function itself, negation of the function, the proportion, the constant of proportionality is minus 10, basically y prime equal to minus 10 y. So, the derivative, which function will satisfy such an equation? In the entire version of mathematics, only one function satisfies the problem, that the derivative is equal to itself, or derivative is proportional to itself, that is e raised to alpha t. Here alpha is minus 10. So, the exact solution is y value at time is e raised to minus 10 t. So, this is the exact solution of the given differential equation. The step size I can take it to be 0.01. So, y naught is given, that is the initial condition, y naught at 1. So, exact solution is computed at a consecutive step size at 0.01, 0.02 and 0.03 and 0.05 like that, and this is the exact solution value. And now, using Euler's method, it is now computed. So, f is what? Minus 10 y. When k equal to 0, y naught is 1, it is given. When k equal to 1, the next step, y 1 is previous step plus f value at the previous point times step size, which will give you 0.9. So, I can compare that y at 0.01, the exact solution is 0.948, the approximate solution is 0.9. When for k equal to 2, y 2 is computed from y 1. So, y 1 is just now we computed. So, the previous value plus f value at the previous point into multiplied by the step size, that is 0.9 plus the f value multiplied by the step size, which will give you 0.810, and if you carefully see that the exact solution is 0.887, the approximate solution is 0.810. Similarly, the third step is calculated, the y approximate solution value at the third time step is calculated from the second one using the Euler's method, that is the y value at the second step plus the function value at the previous second time step multiplied by the step size, and that will give you 0.7290. You can verify with the exact solution. The exact solution value at 0.0 is 0.748, but here it is 7290. In a similar manner, you can go for y 4, y 5, the approximate solutions happen to be 0.6561 and 0.5905. You can compare with the exact solution. Here there is a error, more error, okay, and this is the algorithm. So, knowing the initial value, we compute the time step is taken to be, this is the particular code for the previous problem. In the previous problem, y naught is 1 and the step size is 0.01. So, for t equal to 0 to 1, 0.01, how many interval? 1 by 0.01, which you will get 100 iterations are computed in this code. Okay. So, y naught is 1, and for I equal to from second onwards to the length of t is the length of the interval 0 to 1. So, we are computing the right hand function, and y at approximate solution at the ith variable we are computing, and finally, we are plotting that. Now, I present the pseudo code for the general situation. I will explain. This is the Euler's method. You need y naught, the initial data, and dt the step size, and f the right hand side function, and length of t. Length of t is maximum step size or the number of iteration we are going to apply. The input y naught is initial value, dt that is equal to h the time step, and fi is the right hand side function, and length of t is maximum step size in t direction. the output is y value at any nodal point x I, and x I is often called as nodal point and y of x I is nodal value, and that we have to compute for 1 to the maximum number of steps. So, the code is initialize y naught as the initial value y 0, y of 0 is y 0, then this is the main code, very simple 2 line code of the Euler's method for I equal to 1 and I less than or equal to the maximum iteration and I plus plus increment. Do this, the y value, the approximate solution at I plus 1, that is evaluated in terms of y value at the previous I and f value at previous value, then next I, and finally once you get, use plot that solution, exact solution and the approximate solution. And now I move to the other method called a fourth order Runge-Kutta method for the same problem we are discussing. And why it is called fourth order? The error is often expressed in terms of the power of the step size h. So, Euler method is not of a fourth order method, but whereas Runge-Kutta method there are two variants, one is second order Runge-Kutta method and fourth order. The one which we are discussing is fourth order. So, which will give you approximate solution in a better form than the Euler method. So, basically dy by dx is f. So, y is given in terms of the integral of the right hand side function. So, and I can express the integral in the weighted average manner. So, from this equation I can write y I plus 1 minus y I by h. This is basically derivative of y at I plus 1. So, same thing is given in terms of k 1, k 2, k 3, k 4 in a weighted average value, where k 1, k 2 are given in terms of f, f is basically the derivative. So, the method coincides with the meaning, the derivative is given in terms of weighted average. First we compute k 1, the function right hand side function value at x I y I, then k 2 is the next immediate increment, x I is incremented by h by 2 and y I is incremented by k 1 h by 2. And k 3 x I is incremented by h by 2, y I is incremented by again k 2 h by 2, and k 4 x I is incremented with h, y I is incremented with k 3 h. So, after computing k 1, k 2, k 3 and use the weighted average formula and add with the previous value and you get y I plus 1. And this method is of having error of order h power 4. If h is a small step size, h power 4 will be again with a minimum error. So, this is considered to be a better method. And now we will consider this example. You have dy by dx 1 plus y plus x squared, and this is the right hand side function. The initial point is, this is the initial point 0 and this is the initial value 0.5, and step size is taken to be 0.2. For this problem we compute y value at point and y value at 0.4. This is the equation and this is the initial value and this is the step size, a right hand side function, x naught is 0, y naught is 0.5, this is given. So, using this you calculate f 1, k 1 is function value at x naught comma y naught. So, f is what? F is 1 plus y plus x squared. So, now you substitute here, the k 1 is 1.5. Now, we compute k 2, f incremented with half h, y naught is incremented with half k 1 h. So, here y naught we know 0.5, k 1 we know 1.5, x naught is 0. So, basically if I substitute in the right hand side function. So, y is what? This is a y term, y naught plus half k 1 h. So, h is what? 0.2 and k 1 is 1.5. So, if I simplify it will be what? 0.15 and now x naught is 0. So, if I substitute I will get k 2 as 1.64. In a similar manner I compute k 3. The x component is incremented by half h, y component is incremented by half k 2 h. So, I get this value substituting, I am getting k 3 as this, and in a similar way k 4 f at x naught is incremented by h, y naught is incremented by k 3 h, and using the right hand side function value and I substitute 1 plus y naught with this and x naught plus this, y naught is 0.5, x naught is 0. If I substitute I get 1.7908. So, this is my k 1 and this is k 2 and this is k 3 and this one is k 4. So, if I take the weighted average of k 1, k 2, k 3. So, this is the weighted average and add with the previous value, I compute y 1 and this happened to be the approximate solution values. Now, I go for the next time, h is taken to be 0.2. Now, using the function value at previous y 1 and x 1, I am calculating k 1. K 1 is f value at the previous time step x 1 y 1. Using this f function, here we will put y 1, here we will put x 1 and we get this k 2. F is incremented half h, the x component is incremented half h, y component is incremented by half k 1 h and we get this, and k 3 f component is incremented by half h, y 1 is incremented by half k 2 h, and k 4 x component is incremented by h, y component is incremented k 3 h, and I get this. Then after substituting I am getting these values. For this problem with this initial condition and using fourth order Runge-Kutta method, and this is the initial value and this is the first step value and this is the second step values. Now, I will explain the pseudocode. The pseudocode Runge-Kutta method, this is the initial condition, this is the time step and this is the first, the right hand side function, and T max is the maximum iteration. So, I will once again I will explain the input, y naught is the initial value and dt is equal to h the time step, and f of x I y I the right hand side function, T max the total number of steps in t directions. So, output is y value at I x I for every I from 1 to t max. So, initially I will assign y 0 at the initial value and this is the code. For I equal to 1, I value can take to the maximum number of iteration time steps and I plus plus. So, you compute k 1 and you compute k 2, you compute k 3 and k 4, then the present value y approximate solution value of y at the present one can be expressed as the previous value plus weighted averages. I once again the algorithm y at 0 is assigned as the initial value and this is the main algorithm. I from the first time step to the maximum t max and I is incremented, you compute k 1 f value at x I y I, that is the function value at the previous nodal values, and k 2 K2 is calculated by evaluating the right hand side function at xi incremented with half h, yi incremented with half k1h, and k3 again the right hand side function is utilized with xi incremented with half h, yi there is a difference incremented with half k2h. Just now we computed k2, we are utilizing here. Now k4 is computed as the right hand side function value at xi incremented with h and the yi component incremented with k3h, where k3 is recently computed. So, knowing k1, k2, k3 value, these are the slope values, and this is the formula, the average slope values. You can see that weighted average, you can add the weights and you can divide by 6, it will be 1, you can see that. So, this is the weighted average slope values plus the previous value, we will get the approximate solution of the current time level, and you repeat this procedure for I equal to 1 to the maximum number of time steps, but every increment time steps, at the end you plot the exact solution and the approximate solution. See, why do you need a numerical method? Very often the exact solution will be in terms of an exponential or a series solution even. Okay. So, we need to go for a numerical technique to compute the approximate solutions for this problem, and numerical methods enable the concept of simulation based engineering. Okay. So, in this lecture we discussed Euler method and Runge-Kutta methods to generate simulated solutions without need to calculate the higher order derivatives. One can compute the approximate solutions. I will give a few additional questions to the students. Solve this problem with the initial value and step size from xi equal to 1 to xi equal to 5 using Euler's method and Runge-Kutta methods. So, the students can write a code. Basically the algorithm is very simple. Knowing the previous time, the approximate solution value at the previous time level xi, and the right hand side function, you compute yi plus 1, that is the current approximate solution at the current time level, and this is continued till we reach the maximum time value or the number of iterations, and you will get these values and you plot it. So, write just a few lines, 4 lines code based on the pseudo code, that is an algorithm. The students are advised to write a code and run it on the computer, and you can also perform different case studies and difficult problems you can take and implement in the computer. So, I thank the students for patiently listening to my lecture, and we will meet in the next lecture. Thank you very much.